So first, a little bit of background about DSSD. This was a company that I was one of the founders of back in 2010. And the problem we set out to solve was how fast could we make a storage system? Could we actually make the fastest thing ever? And what are the actual obstacles to doing that? And the reason for that is two words I hate more than any other in the world. I'm so tired of hearing about big data and the Internet of Things and data lakes and all this jargon. And it's like, yeah, data's big. We all know that. But how are we actually going to process it? What do you actually do with all this big data? And we wanted to go back to first principles and say, look, everyone talks about different workloads, right? File systems, databases, sensor networks. You think about life sciences, genome sequencing, autonomous driving, all these things generate lots of data. But back to first principles, really all computation is actually the same, right? To get any kind of result, you perform math on data. And if you want to get results faster, then you need faster math and you need faster data. And I don't care what your workload is, you know, the ratio of math to data might be different. Matrix multiply, it's cubic to quadratic, and other searches are linear, and index things are logarithmic. But fundamentally, you're doing math on data. So how are we doing on actually making math and data go faster? Well, this is from Hennessy and Patterson. CPUs now are about 20,000 times faster than they were in 1980. Right? We've had an enormous run-up, especially during the 90s. That was when we went from megahertz to gigahertz. That was a great decade. It also meant that we got a little bit lazy in software because CPU was coming faster than we could waste it. But on the I/O side, disk performance didn't even close to keep up. On the one hand, capacity got tremendously better, about a factor of 100,000. That's great. Bandwidth has gone up about a factor of 100, and IOPS only about a factor of 10. And so if you plot these against each other, IOPS and bandwidth versus MIPS over time, and normalized to a 1.0 ratio in 1980. So this is, you know, Seagate ST506 versus a VAX 11780, right? We'll call that ratio 1.0. We've actually had IOPS and bandwidth per MIPS go down relative to CPU, so much so that by the time you get to about the year 2000, that ratio is virtually zero. If I actually put the numbers out, it's about 0.0003. So this is why when flash arrays came out, it was such a big deal, because that got us from having a ratio that was near zero to where the IOPS per MIPS is actually now competitive. Got a little bit of feedback here. Is actually now competitive with where we were, 30 years ago. Bandwidth's still lagging. And then what we did with the SSD is, and I had to sort of rescale the axes here, is get IOPS per MIPS to actually better than it was back when Jimmy Carter was president, which is, that's something. And we actually got the bandwidth per MIPS up to parity. So just to sort of summarize the numbers for our first product, if you look at where was hard drive performance versus DSSD, taking CPU as your baseline, capacity up by a factor of 20 million. Of course, that's likewise for disk drives as well. But bandwidth is up 20,000, IOPS is up 200,000. So this is really great for big data problems. But of course, what this talk is all about is how, right? How do you actually get that level of performance out? So again, we're going to go back to first principles. And we started with, when we started the company, just looking at, let's get a data sheet for a flash chip and ask the question, how fast does this thing go? Well, it turns out that to read one page off of a NAND chip takes under 100 microseconds. And that implies that if I can do that multiple times in a row, I should be able to get 10,000 IOPS out of a single flash chip. And if you're doing 32K reads, which on the generation we were looking at was the most you could read at one time, that implies a bandwidth of 320 megabytes a second, again, from one flash chip. Now, in an SSD, you actually have many flash chips. And in fact, what you think of as a chip, the package that it comes in, is typically not a single chip. It's actually a wire-bonded or TSV stack of anywhere from 2 to 8 currently, and that's actually going up as well. So with 64 packages, you can easily get 512 NAND die in an SSD form factor. And if you just multiply that out, that implies that a single SSD should be able to do 160 gigabytes a second, okay? Now, reality is only about 1% of that. So why? Where are we losing all that performance? Well, there's a number of things that actually limit you. One of them is just power and cooling. It turns out that flash actually takes a fair amount of energy because the way you read it is there's a charge pump inside that builds up a voltage, and then you sense it. And it actually takes a fair amount of power, not only reading, but also writing and erasing, fairly power intensive. You're actually limited in your SSD form factor by two things. One, your ability to deliver power to the device, but the other, to be able to cool it. And NAND is unfortunately very finicky about what temperature it likes to operate at. And it's not even as simple as it likes to run cool or it likes to run hot. It's faster to program when it's hot. It retains data longer when it's cool. There's a whole bunch of trade-offs involved that are very annoying. And so you want to be able to control that. Unfortunately, in an SSD package, you really don't get to do that because if you've got a couple of circuit boards in there and you've got two surfaces on each, the chips on the top surface here and the bottom surface there facing outward to the enclosure, you can cool. But the ones on the inside surfaces facing toward each other, that's just dead air. So not only is it hard to cool, but you can't cool it uniformly. So the form factor is a problem. Another one is the flash channels. Right? We saw on the previous slide that each individual flash chip can do about 320 megasecond, but the flash channels that they're all connected to can only do about 400. So roughly speaking, one flash channel can handle about one flash chip worth of bandwidth. But because of the sheer number of wires involved, you typically have many flash chips per flash channel. Anywhere from 4 to 16 is typical. Then you've got another crunch on your bandwidth, which is that anywhere from 8 to 32 flash channels, depending on your flash controller, are sharing a single 12 gigabit, which is only 1.5 gigabyte SAS interface. So you've gone from this 160 gig a second potential number, sliced it by roughly a factor of 10 because of the flash channels, and sliced it by another factor of 10 because of the SAS interface. And then on top of that, the software stack adds a huge amount of latency, and I'll break down the numbers on that in a moment. So there have been two main approaches thus far to using flash, and they're sort of the ones that you might expect. One is to say, on the left side, we're just going to make an all-flash array, right? Because this is sort of the same reason that everyone making a storage product starts by making a block device, right? You make a block device because every application can speak block. It's a well-known thing, as opposed to coming up with your own API. So you want to make an all-flash array? Great. You take flash, you put it in an SSD form factor. It looks just like a disk drive. Put it in an array, run your existing RAID stack, and you have all your enterprise storage features, hot plug, all that good stuff. But you've got a lot of latency, and you're piping everything down through these very small, little soda straws relative to the lake of data you're trying to access. On the right side, you have the sort of Fusion I/O type approach of saying, I'm going to put storage in the server. I'm actually going to take flash, put it on a PCI card, plug it directly into the server, cut out a whole bunch of the I/O stack. So you're cutting the latency way down, and you're getting the bandwidth up because you've got a lot more bandwidth with PCI. And that's great for latency, but you have a couple of problems with it. One is that the storage is now physically inside the server, which means from a serviceability perspective, that's a nightmare. It means you don't have RAID across multiple servers, so you don't have any kind of data protection. So it's really good if you want to make something that's like a cache, where you're not worried about persistence, but it's really not great for making an enterprise storage product. So we asked the question, is there some way to get the best of both of these worlds? And looking forward, the approach on the right seemed like that's closer to the architecture you want to end up with. So we said, all right, let's start with the server-attached flash model, where you got a bunch of servers, they got flash cards inside. And how can we make something out of this? Well, first we're going to pull the flash out. Okay, so the flash is now outside the server, and I didn't show it on this diagram, but there's actually a little PCI card still inside the server that's basically like an HBA. It's not really an HBA because HBA is host bus adapter, and there's nothing to adapt because it actually is the host bus. It's PCI. But there's a card in there. So we now have connectivity between flash and server over a PCI cable, except so far we haven't solved the problem of stranded storage. So we're going to direct connect all the compute to all the storage with a PCI fabric. So you take some switch chips, and this is a simple two-level fabric here. And now every piece of storage has direct connectivity over PCI to every server. But we still haven't solved data protection. So let's add enterprise RAID, hot swap, all the things you would expect of a storage product, and let's call that rack scale flash. Right? So that's what we termed this new segment. And the idea is we move the flash out, we add RAID, dual porting, all those things you'd expect. All the clients can see all the data. So just like with a flash array or a hard drive array, all the data is shared. And in fact, in some sense, you can almost think of the box we built as it's like a 96 ported hard drive, right? It's just you can plug lots of things into it and see all the data. But it turns out, because flash is physically very different from disk drives, that there's a lot more you can do with data protection, concurrency, and software. The basic design element here is really simple. So in the middle, you have your blue PCI switch. That's what connects everything to everything. In green, you have a client. It wants to do an I/O, so it sends a logical request, and we use NVMe as a transport, so it's very low latency. Just basically a 64-byte posted write over PCI. Boom. You send your request to the CPU that lives inside our system. It looks up that object at offset and says, where does that physically live on flash? Sends it down to the appropriate flash module, that's step 2. And then the flash module has a DMA engine and DMAs, again, over PCI, directly back to the client. So the CPU in this picture is not involved in any kind of data processing. It's strictly the traffic cop to manage the flash translation layer that tells you where logical data resides physically. So that's the basic design element, and to make our D5 system, all we did is replicate that. So this picture here, if you look at it, it's the same thing. These little blue rectangles up here are the client ports. The gray diamonds are PCI switch chips. You can see it's a full mesh, everything to everything. We've got some just good old-fashioned Intel CPUs here, and these represent the flash modules. So when an I/O comes in, client sends it down to the first tier, second tier, over to the CPU, looks it up and says, oh, that's on this flash module over here. So from this CPU, we go out to the switch, down to the flash module, and then we then DMA the data up to this switch, over that PCI crosslink, out to the client. Very, very simple data path. And because pictures are always fun, here's what that full mesh fabric board actually looks like. This is actually one of the earlier revs, but it basically has the same physical structure. These are IDT switch chips, or PMC switch chips, or microsemi switch chips. And just like we are DSSD, or EMC, or Dell, I have to update the slides title more often than the content. So there's our fabric. And then kind of what this looks like in terms of how the overall system is put together is, here's the fabric back here. Here's our mid-plane, this is passive. You have a control module up front, that's got your CPUs. And then here is one of 36 flash modules. That's where the data is actually stored. Now, the thing about those flash modules that's really nice, you'll notice that that board is very long and skinny and thin. And what that allowed us to do is the flash module is actually much simpler physically than an SSD, because all it actually has on it is this diamond here is the IDT / whoever acquired them twice. That's the IDT Princeton flash controller. It's got 32 flash channels, and these are the NAND placements. This was a very early rev of the board, so we actually didn't have it fully populated, but all those slots there are for flash chips. And so what you have is just, and it's the same on both sides. So you have this very thin PCB, flash chips on one side, flash chips on the other, a thermal interface material, and then the aluminum housing. And what that gives you is this extremely uniform thermal environment for the flash to operate. So just a quick summary of what the box actually looks like after we skin it and make it look pretty. About 10 million IOPS, 100 gig a second. And I should mention too, if I go back a couple of slides, This picture here is the output of a simulator that I wrote to model different ways we could architect the box. Because we were looking at different numbers of switch chips, different numbers of PCI lanes between them, and I realized pretty quickly that doing this on the back of a napkin was just, it was going to take too long. And it was very, very error prone. So when I finally got the simulator working and I started running some numbers out of it, and I saw this 129 gig a second projected bandwidth. This is back in 2011. And I just thought, okay, I must have screwed up. Right? There's got to be a mistake here. I'm off by a decimal point. But I finally convinced myself by a combination of looking at the code and then just back of the envelope calculations, yeah, it actually should be possible to go that fast. There really is that much bandwidth when you have that much PCI. So there's the box. Now, that's the hardware. So what about the software? Well, the software is a whole other problem. So inside that box, we've got 32 cores to run our I/O stack. Those 32 cores, we need them to drive 10 million IOPS, right? So that's 300,000 IOPS per core, which means you've got 3 microseconds per IOP. Now, if you've lived in this disk-based storage world for a long time, which I did previously in ZFS days, that's a terrifying number. And the biggest thing that we worried about when we started the company is is there any possible way we can get the cost of an I/O down that low? It's really just a handful of instructions and cache misses. Is this even possible? Well, the first thing we realized is we're going to have to eliminate layers like crazy. And even things like just trapping into the kernel to do a system call, taking an I/O completion interrupt, no way that's going to fly. Fortunately, we weren't alone in having to solve this problem. The NVMe protocol is really an absolutely key enabler for what we do. Because what you can do with NVMe is instead of having to do a system call and get yourself into kernel context every time you want to do something, you can actually map stuff into user space, okay? And the model that we have is that so in NVMe in general, you have submission queues, completion queues. So you want to do something, you put a 64-byte command packet on a submission queue, ring a doorbell, and then the other side goes off and deals with it. And likewise, you have a completion queue where you get these 16-byte completions coming in. Okay. Well, the great thing is that PCI, being something that you can use for memory mapping, allows you not only to have this sort of load store access model inside the box, but also over PCI cable across boxes. So what we actually did is we took the submission queues and we put them inside of our D5 server. The clients then map that memory into their address space, and we're protected by NTBs, and I don't want to get too much into the weeds. But basically the idea is that there's a piece of the D5's address space that's mapped into the server that wants to talk to it. It just does a store, so it's a posted write over PCI. The reason that's important is you never want to do reads over PCI because they're slow. Posted writes, of course, have another problem, which is that you don't know if they succeeded, so there's a whole bunch of other complexity, which again, I'll save for over drinks or something. But you do a posted write to the SQ, which lives in our server space, and then the completion memory, those CQs live in the client space. So when the I/O is done, we DMA, and then the completion goes over PCI, again, by posted write to the CQ in client space. On both sides, we're not dealing with any MSIs or any interrupt processing. It's all polling based, because if you want to go high speed, you've got to be doing polling. We learned this in networking 10 years ago or more. This is what the initial diagram of the software stack looked like. Turns out that wasn't actually too far off. This was in a Pete's Coffee in San Mateo, November of 2010. That was sort of our critical month. So components of I/O latency. So I mentioned before, we're going to get down to the breakdown here. In an SSD, right, you're talking to flash. So part of your latency is just the time it takes to read the data from the flash. And that's basically because you're sending a series of sensing pulses, and then you have to get the data from the flash chip, from the actual flash cells into a page register that's in the flash chip. Then you take that data that you got from that, in green here, you clock it over the flash channel. That takes some additional time. Then you run your ECC to correct errors. In red, I've got the firmware cost, and in yellow, the DMA cost. Now, interestingly, the cost of DMA is really, really low in this picture. The two things that dominate are really, I guess, three. There's the media access time, which one thing we decided not to do is be in the business of making media, because that's really hard. The software cost is the number one thing. And then time the clock over a flash channel is significant, but not dominant. Now, in DSSD, we, of course, don't get any better latency from NAND than anybody else. It takes what it takes to read from the NAND. Clocking, with Princeton, we got slightly better flash channels, so that's a little bit less time. Our firmware cost is actually about the same. But then our software cost, because here's what's interesting. The software cost is only 3 microseconds, but we didn't actually get to that because we were trying to solve a latency problem. This is totally backwards from how things normally happen. Normally, you have bandwidth first, and then you want to get latency, right? Because bandwidth is easier, right? Bandwidth is the work of man. Latency comes from God. So, but we actually had the reverse problem, which was to get 10 million IOPS, which was the actual goal. We had to get the latency down because we only had so much compute to go around. So it was actually the bandwidth that was driving the latency down. And to be honest, the fact that the latency is so low relative to the cost of NAND in the current generation of technology doesn't really matter that much. If that number is at 3 microseconds, it was 10 microseconds, it wouldn't really change our performance much. Where it really starts to matter is when you get to some of these next-gen non-volatile memories, where the media access time now gets into single-digit or even sub-microsecond. You still got clocking time, you still got DMA time, a little bit of firmware, but this is where having the software cost down is really going to be key for us going forward. Now, I mentioned that flash is physically very different than disk drives, and there's a couple ways in which that's true. One is that disk drives, and I'm oversimplifying when I say this, but typically disk drives fail catastrophically. There are, of course, bad sectors and transient vibrational problems and all that, but basically hard drives fail catastrophically and you lose the whole drive. It's a head crash or whatever. Flash has a very different set of failure characteristics. The good thing about disk drives, although they're slow, you can read and write data over and over and over again as many times as you want. It basically never wears out. You're going to lose the motor long before you lose the magnetic properties of the media. Flash, though, you can only program and erase tens of thousands of times. It's really not much. And in fact, there's an aspect of this that's, I'll take a little detour here. Because of the fact that you can only program and erase flash a certain number of times, what that actually means is that your ability to have flash last for a useful amount of time is directly related to the capacity, right? Because a given cell can be programmed and erased so many times, and if I multiply that by capacity and divide by bandwidth, I get the lifetime of the data. So the fact that PE cycles affects lifetime is sort of obvious. The fact that more bandwidth, more write bandwidth equals less lifetime, which is why it's in the denominator, that's obvious. But that capacity in the numerator of that formula is a little bit sort of counterintuitive. And what it basically means is that if you have a big all-flash array, it's going to last way longer than a thumb drive, simply because the thumb drive has so little real estate, and you're rewriting the same cells over and over and over again. Whereas on a flash array, you have to fill the entire thing up and then circle back to the beginning before you're going to go through another PE cycle. So capacity actually solves the PE problem to a certain extent. So flash also has this property that it degrades over time. So when flash is new, you'll have, and this varies from vendor to vendor and generation to generation, but in rough numbers, when flash is new, you're going to have about 1 bad bit out of every 1,000 that you read. Could be 1 every 10,000, but roughly it's going to be 10 to the minus 3 to 10 to the minus 4 kind of error rate. At end of life, it's closer to 10 to the minus 2. So 1 in 100 bits are bad. So you need a lot of ECC correction. So fairly typical is for every 1,000 bits of data, you've got anywhere from 40 to 80 bits of ECC for correction. And it's either BCH or LDPC. So it's much stronger than what you can do with RAID, because you just have so many bits that are failing, and they're failing randomly. And then there's also, you like in disk drives, when you have adjacent tracks, right, a write on one can interfere with the guy next to it, right? Well, in NAND, you have the same kind of problem with different adjacent lines, and you have even problems of like, if you have all ones or all zeros, that creates a higher voltage in the cell, and that can cause problems. So every flash controller has a scrambler built in to randomize the bits so that you have a roughly even mix of ones and zeros. And you actually want to change what you're randomizing with each time you program it in case, because otherwise you get the same pattern. And if you have the same data, you scramble it in a predictable way, you get the same pattern, and that causes more wear. So that's bad too. Flash is basically garbage that it barely works. We tolerate it because it's really fast. I mean, you can sort of see it say the same thing about disk drives or tape, really. It's all crap, but, So the other thing that's different, though, is, you have vastly more discrete devices when you're dealing with flash, right? So we have, in our D5, we have 18,000 NAND chips, right? As opposed to like an array of 25 SSDs. So you look at that and you think, well, there's certain things that implies. Like one, from a performance perspective, I don't really want to think about queuing the same way, right? Like I queue IOs to a disk drive, and I have a fairly deep queue. Why? Because you want to take advantage of the fact that if you queue up multiple IOs, the disk can internally sort those such that as the platter spins, it can move the head and catch more than one thing on each revolution of the platter. For NAND, it doesn't matter. There's no difference between sequential and random IO performance at all. So that changes the way you think. It also means you want much shorter queue depths, because I've got 18,000 devices I'm queuing to rather than a couple of dozen. But also enables a new data protection model, right? This is really not like a disk drive, right? This thing where inside what's behind the flash controller, there's hundreds of individual devices. What do I want? With 64 chips, a 64 wide RAID stripe, that's probably not the best I can do. So we introduced multidimensional RAID. And the idea here is that because there are so many different targets, instead of having a RAID stripe, which is a one-dimensional thing, what if you had a two-dimensional grid? How would that be different, right? So one way to think of it is just it's a layered RAID of RAID, right? So you could have RAID inside the flash module, and you could have RAID across flash modules. But we can actually do better. So let's just walk through what RAID reconstruction does. So brief reminder, RAID 6 is double parity RAID, can recover from any two errors in a stripe. So let's say that I have cell 2,5 here in this two-dimensional grid, and that fails, right? So I read the rest of the stripe, and let's say we try to solve across the row D2, and maybe we have another bad cell as well. Well, that's okay, we got RAID 6, so we can actually fix 2,5, and we have our data back, right? But what if I get a pattern like this? If I want to try and solve across the row, it's 3 errors, RAID 6 can't recover that. And if I want to solve across the column, can't handle that either. But if instead of thinking of these as two independent RAID dimensions, we thought of it as one unified grid, we can do better. We can take sort of a Sudoku approach. We say, well, I couldn't solve the thing, but I can read row D0 and I can solve that. And once I solve that, now column D5 has gone from 3 errors down to 2. Now I can solve that. And this turns out to be incredibly powerful. This is recoverable using Sudoku-style RAID, right? So let's do it, right? We'll solve row D0, and none of the other rows are solvable. They all got multiple, more than 2 errors. So now we switch to columns, right? Column D1, fix that up. D2, D3, D4 I can't fix, but then 5, 6, and 7, those are all 2 errors. We fix those up. And now we go across rows, because those are only 2 errors. And we got all the data. Thank you. So the multidimensional RAID properties are kind of interesting. The only kind of pattern that it can't solve is when you have a perfect grid. So like a 3x3 grid there's no way to start the Sudoku process when you've got an error like that. So the smallest unsolvable thing is when you've got a perfect grid of m+1, if m is the parity, m+1 to the d power, where d is the dimensionality. And of course, as we saw in the previous slide, much larger asymmetric patterns are solvable. Whereas if you're doing linear RAID, in the same amount of space, it's only m times d failures. right? And basically what you're doing here is you're taking advantage of the fact that when you go to higher dimensional spaces, they're sparser. And that just has a whole bunch of nice mathematical properties. And why, you might ask, like, why don't we do this? Well, all right, I'll get to that in a second. So the mathematical properties of 2D RAID turn out to be really, really nice. I won't make you read this, but I'll just sum it up as this. In your parity grid, so in green, I've got the data. In yellow, there's your P and Q, okay, across rows. In blue, that's your P and Q down columns. The obvious question is, for purple over in the corner, what do you put there? Do you put the parity of these guys, or the parity of those? Or do you take like those plus those, or what do you do? It turns out, because linear algebra is awesome, that the parity across the rows and the parity, down the column and across the rows, they're equal. So you can use these purple squares to solve either row or column defects. So you don't have to treat corner parity as though it's something, like it's some kind of special case. And if you want to just think of it in terms of linear algebra, so the French, by the way, have a much better way of teaching matrix multiply than we have in the US, right? So in the US, remember how you learn matrix multiply, you write the three matrices side by side, and you can never remember which way the dot product goes, right? The way they teach it in France, and I learned this back at a guy I worked with years ago, is you put the matrix you want to multiply, the two matrices, you put them in this position, and you put the product down here. So I want to do C times D. It's really obvious which way the dot product goes, because it's, if I want this spot in the result, it's the dot product of this row and that column. Everything just lines up. So that you go across, you do your dot product, and they converge where the answer goes, all right? So if C is my column parity generation matrix, C times D is the resulting actual column parity. If R is the row parity matrix, D times R gives me the row parity matrix. If I wanted to do column parity of the rows, I would take C times DR, which gives me CDR. And if I wanted to go the other way, I would take the column parity times the row parity matrix, which is also CD times R, because matrix multiply is associative. That's what I meant about linear algebra being awesome. Now, finally, why hasn't this been done before? Well, it turns out the actual reason is, more than anything, I mean, maybe people didn't think of it, but maybe somebody thought of it and realized it just wasn't viable. Because when you're doing this for hard drives, you're thinking about, let's say, 10, 20 drives. Let's call it 16. Look at this lower corner here, this lower 4x4 region, right? That's what the matrix would look like if I had only 16 drives. So I'd have 4 data drives, those 4 green ones, and 12 parity, right? That's terrible, right? It's only as you have very large numbers of devices where you're doing this that this becomes space efficient. And it's actually about 17% overhead to do two-dimensional RAID with 18,000 things. Okay, so we've got 5 minutes left. I'll stop here and open it up for questions. Yes? Oh, she's bringing a mic over. Thanks.
Can you elaborate on the performance implications of, for example, an update on such a mechanism? Because basically, when I update just a single block there, I'm affecting like both dimensions, right?
Right. So the thing about Flash is that, unlike with disk drives, Flash can't be overwritten. You have to erase it and then reprogram. So everything in Flash is like copy on write style file system. So when you're generating a RAID grid like this, you're always starting with a completely blank slate and filling in new data as you go. So you would never update it in place. Yes?
Columns and rows to be parity checked. Does that have impact on the latency of, or when is that done? Does it affect in the background, or does it happen in the? Does it affect the end user?
Oh, I see. Yeah. So RAID generation is a background task. Basically, the way it works is, let me go back to this picture. So I didn't get into this because it's a little bit in the weeds, but when writes come in, as you might expect, we don't actually write directly to NAND, we buffer the write. So every flash module has a supercapacitor in it to back the small amount of DRAM that's in there. So what happens when you do a write comes in, and where it actually goes is it first comes in from the client, hits this first PCI switch. When it hits this second PCI switch, this is programmed for multicast, and it will actually go to the CPU and to a pair of flash modules. So we're sending it off to 2 flash modules, so we have 2 copies of the data in case they both fail, and there's a third copy sitting in CPU memory. So as soon as the data has made it out to the flash modules in memory that is supercap backed, we can commit the write at that point. Meanwhile, we're building all those writes up, and as they come in, doing the P and Q calculations, and once we have an entire grid, that's when we take the memory, the DRAM inside the flash modules, and program that all to a grid of NAND pages.
It seems like the recovery is going to need more compute resources.
The question was, it sounds like recovery would take up compute resources. That's true. The good thing about that is that this whole little algorithm here, let me go back to sort of the beginning. So here's a grid of cells. So the most common thing that's going to happen is that when I go to read any cell in this grid, the read's going to succeed. Right? That's the number one most likely thing. So in that case, let's call that the 99% case. I get my data back. Sometimes there's going to be more bad bits than ECC can recover from. So I'm going to have a bad cell. So I'm going to do just a simple P reconstruction across 32 columns or 18 rows. It's going to be fairly rare that I actually get this scenario. The whole purpose of solving stuff like this sort of Sudoku RAID approach is that it's not that you are going to solve a pattern like this in the common case. That's going to be extraordinarily rare. But what it does mean is that I add a whole lot of 9s to the reliability of the NAND. Because on the one time in a blue moon when that happens, I don't lose data. Yes?
This will be the last question.
In your 2D parity design, if the position of the corner parity is a bad block, where would you put your corner parity in?
If the corner parity is
A bad block.
a bad block? Oh, great question. So in this, I'll use this picture. I'll use this one. I've shown it kind of the standard like RAID 4 way of drawing things. That is to say, it looks like P and Q are in a deterministic location. In reality, like RAID 5, we rotate the locations of P and Q both in the column and in the row axes. But furthermore, in addition to the normal rotation that goes on, before we decide where we're going to place parity, we do a defect count of all the cells, and we put the parity in the least defective rows and least defective columns that we can. Because unlike, say, a defective data cell, which we simply don't use and omit from the RAID grid, we treat it as just a page of zeros, a defective parity cell, if you're obliged to put the parity in that location, you have no choice but to logically put it there, even though if you try to read it, the read's going to fail. So by doing this defect avoidance, we make the probability of that extremely low. But it can happen, and when that happens, you just rely on the fact that the parity cells are in some sense they're not in any other way special. They're just part of the data that you need to reconstruct a row, and you go through this Sudoku process to get the data back. Okay, thank you very much.